Okay, perfect. Welcome everybody. Today's class is complicated. I mean, coding Irradiance is not something I haven't seen many engines that don't have this feature because it usually is complicated. I mean, I found this solution that I'm going to explain today, which is I think well, not the best one, not the worst one. It's you can implement it. It has problems and it doesn't work for all kind of scenes, but at least you can use it now on your engines, and it's a good first introduction to Radiosity. So I think it could be interesting to code it. So let's see what we have now. Currently, we have this crappy engine. I call it during the classes, so it's still a lot of features missing. This doesn't have basic things like PBR. It doesn't have the ferret is very badly written, so don't pay too much attention to the code while I'm working. Remember, this is the bad example. I just do here to show you the important part, which is the Irradiance, but the rest not. And because during this development of the Irradiance, I'm going to need to use my engine, so don't expect that your engine has to be exactly the same. Always keep the ideas, never the way I implement them, because the time I have is very limited. Also, I have to say that probably I won't have enough time to code everything. I will try. If I don't have enough time, it's okay. I mean, sometimes you don't have too much time to code all the features. Also, I would like, I mean, if I wanted to do it right, I would probably create an entity here that is some kind of new entity. Like we have now the prefab entity and the light entity. It would be nice to have a new entity, call it Irradiance cache. Maybe I'll do it if I have some time at the end, but I don't think I will have to have my own special Irradiance cache that I can move around in the editor. As I can move the lights, it would be nice to move the cache because maybe I want to align all the objects right. For now, I will hard code a lot of things, and if you have time, you can always clean up and create new entities. I think it's interesting to create new entities for the engine because it's a good example of how you can extend it in the future. But anyway, so let's start to see what we need. Okay, so first step, always go to the slides, and here there's a lot of interesting information. Let's go down here probably. Okay. Well, I don't know where to start because here I have the link. Yeah, here. I'm going to need to bring code that's also from other places, but let's start here. Here do you see there's a file called sphericalharmonics.h. I think I put this file on the engine. Here it is, yeah. Because previously you have to copy it, but I thought it would make more sense to have it. It's just a tiny implementation of the basic thing that we're going to use, which is first a way to store the spherical harmonics. Spherical harmonics at the end is just 9 colors. As we said, these 9 colors maps the illumination around different areas of a sphere. And it's encoded using this kind of spherical harmonics. And there's also this other function, and it's a function where you pass an image, okay? Sorry, an array of images, 6 images. This is what it says here, it's an array. It has to be 6 images, so it has to be like a cube. And then you can tell if these images came in gamma space or in linear space, which is important when you're going to compute the amount of illumination that you have. And you can see that these images are float images, okay? Obviously, they are float images because if they weren't float images, that would mean that I'm clamping areas of where there is more than one, and that's bad because for this case, we want to capture how much light is in the scene, and the very bright areas are the ones that contribute more to the amount of illumination. So if I didn't use float images, I wouldn't be able to capture those areas, which are the important ones, okay? And here I have this strength function here called cube map face normals. It's just a function I use to know when you're making a cube map, which is the front face, left, up, right, because the order has to be specifically for OpenGL. So here I have mapped the order of the 6 cube maps. What's the target and the front and the right vectors, I think, if I recall correctly. Anyway, we are going to need to use these functions but now let's start with the very basics, okay? So let's start by the concept of what we need, and then we will extend it to go beyond. So for now, I want to capture how much light do I have on one specific point, okay? How much light? So I'm going to need probably some spherical harmonics. So let's go to my renderer here, and let's allocate some memory to store those spherical harmonics. So I can include the spherical harmonics thingy. Is in the util, no, GFX. So GFX, spherical harmonics. I'm going to put it here with the rest of the GFX. And now, because I have this file, I can include the spherical harmonic structure, this spherical harmonic. Maybe it should be better to put an S in front. I always like to put S to say this is struct. I forgot to put it here. Well, for the next year, probably I will change it. And yeah, I'm going to allocate memory for one of them. So I have this spherical harmonics, and I'm going to use, I don't know, Irradiance point. I don't know. Okay, but when you capture the irradiance, you want to know where did you capture it. That could be useful in the future. So obviously, besides saying what's the irradiance, I probably want to know where it was captured. So irradiance position maybe, and irradiance could be SH, the spherical harmonics. Okay, and I think if I recall correctly in the slides, I recommend you that you create this track. Okay, so I'm going to do like with this, which is similar. So this struct says, okay, I'm going to prof the space to get information. So I'm going to, yeah, I have to modify this, sorry, because from previous years, I modified the name of the variables. So this, wait, I don't mistake it. Okay. And here probably there's going to be a lot of places where I say vector 3, sorry, I called the function, I changed the name of some functions this year because vector 3 is generic, and I wanted to have vector 3f to say that's a float, and now that's going to bring some problems. But anyway, so let's think what we have here. We have a prof, okay, it has a position. It has also a local position because we are, this prof is going to be inside an array. You remember like this grid, and this says the position in the grid. If, for instance, the first prof, the one on the corner, is 0, 0, 0, the next one is 0, 0, 1, 0, 0, 2, and if you go below, it's 0, 1, 0, 0, 2, 0, etc. And this is the number inside the whole array. Don't worry about this. We will use it later. You will understand. This is just to index the profs inside a big array with where all the profs will be stored, and the spherical harmonics. Okay, so this is a struct, but we want to have one. So let's have a prof here. Okay, and before I capture anything, it would be nice to have a way to visualize what I'm capturing. So first thing I'm going to do, I'm going to try to render, I'm going to create one prof. Okay, so let's go here on the renderer. I don't know, define. Okay, this prof, the position is going to be, I don't know, maybe I can use I can run the application and set up, I don't know, find a position. I don't know, a position that it's in the middle of the scene. I think 0, 100, 0 is a good position, but I'm not sure now. So what I can do is just move something around on the scene until it's in a position and copy the position, so I know where it's going to be capturing. So it's launching the application. Okay, so I want a position like, I don't know, here in the middle. Okay, so let's, I don't know, take this trash bin. Go ahead. Why is not selecting? Yeah. No, I want to select this one. What's going on? It's not selecting anything. That's weird. I think I modified something and now it doesn't detect when I select something. Okay. Anyway, I'm going to move it here a little bit higher. So here in this position, okay. So this position is 66, 65, 64. So yeah, okay, 65, 65, 65. Okay. So I think it's a good position. So I'm going to put the prof there, 65, 65, 65. Okay. And it's not going to have any data now. For now, it's just the spherical harmonics. I don't know. I can maybe, if I want to test, I can put, I don't know, on the spherical harmonics in the 0. Remember that these have some coefficients on the 0. I can set a color here, like, I don't know, red, for instance. Okay, so if I recall correctly, if you set up the first coefficient to some color, all the prof is going to have that color. Okay, so now we have one prof. And next step should be to visualize it. So we need a function to visualize the prof. Always, when you have some data, make function to visualize the data, to be sure that its data is correct. So debug, render prof. So this is not a function that we're going to use at the end. This is just a function to visualize a prof on the screen to see that it's right. And I don't know, I pass a prof here. Okay, so if I call this function in any moment and I say, can you visualize me this prof? It should render this on the screen. Okay, Let's do it. So I don't know, I'm going to put it, I don't know, maybe below this one. Yeah. Okay, so it's complaining about something. What's complaining? Type prof. He doesn't like my sprof. Oh, I think that sprof is defined. No, where's defined the sprof? Oh, sorry. I define it in the CPP. That's a bad idea. You never define extracts on the CPPs. That means, that, well, at least it's only local. But I wanted to have it be accessible from everywhere, so I'm going to put it here. It has to be outside. Yeah. Okay. So now we have a function that we can use to render the prof. Let's go to the function I created. Yeah. Yeah. Here. Okay. So we're going to have to render some mesh, and obviously the most basic mesh is the sphere, so we'll render a sphere. Okay, so let's start with this, but obviously to render a sphere we need to have a shader, so we need a shader, and we are going to call this shader inner atlas because this is a special shader. So let's call it, I don't know, spherical prof, I don't know, just to put a name. And so if everything goes well, we just do the classical thing, enabling the shader, and I'm going to pass a model because we want to specify where is this going to be rendered. So let's call it U model. Where's going to be this sphere? And where's the position? Well, the position is going to be, oh, sorry, I have to put model first. So this model is going to be a matrix for 4, and we don't have to rotate on anything. We only have to translate it to the position of the prof. So the position of the prof is pos.x, y, and z. Okay, so we have the prof in the right position. The problem is that this sphere is only of radius 1, I think, and that's very small. We won't be able to see it very well. So the next step should be to scale this one. So I don't know. Sorry, scale, not set scale. Set scale will destroy the translation. So I don't know. 20, and we can make it bigger later. Okay, so we have shader, we are passing the model. We need to pass everything, like for the camera always. So all the camera to shader, it was camera to shader. Yeah, I here have it. Everything related to the camera. Which camera? I didn't put it here. So always is good to have here the camera. So camera is camera, current camera. Okay, so we have the camera, we pass the model and all the crappy things, the view projection, and if we need anything, and then shader is enabled, so I'm ready to render this sphere. I should see the sphere on the same position where I specify. Okay, simple. For now, we have a way to see a sphere, but we need, obviously, a shader. So let's go here, build the shader. So while I build the shader here, like, I don't know, FS, which kind of shader should I use? The basic VS or the quad VS? So what you think about it? Which vertex shader should I use? Quad VS or a sphere, or no, quad VS or basic VS? Basic, obviously, because we have a model, and this is we are rendering this in wall space. We are not rendering this in screen space as the quads. So for now, I think I'm going to go for the texture.fs because I think this is this closer one to the one I want to render now. So for now, this is okay. Okay. We're going to have all this wall position, blah, blah, blah. I don't know if I need it. I don't have any texture. I don't have any color, no time, no alpha, nothing like that. So for now, let's just go with, for now, let's start by drawing it, I don't know, white, maybe? Everything white. That's it. And we will fill this with all the spherical harmonics thingies. And we don't need UVs. No. The normal, yes, we are going to need the normal to read the position, and the wall position and the position for sure not, because this is the local position. So something like that. So as I said, this makes total sense, and thank you, David and Julia, for answering that one. So it has to be the basic VS because we need the model. We need to take into account that, and so let's put it like this. Okay, so if I think as far as I have coded now, we should be able to see the sphere. The only thing we are missing now is to call a function that calls this render prof. I'm going to go with the forward renderer now. I'm not going to use the ferret one, mostly because, well, I can do it in the ferret one. Well, I'm going to go with the ferret. Let's see. Let me think. Yeah, I'm going to go with the ferret one, and I'm going to render it in the later pass. So when I render it in the ferret, so let's see. The ferret, yeah, this one over here. I'm going to do everything, all the illumination pass, all the lights, blah, 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 blah. And here, I want to see the prof. Which prof? I think I only have one, no? If I recall correctly. Yeah, so after rendering the lights and everything, well, here I'm using full screen quads. So the blending is disabled, the depth test, well, the depth test is disabled. I want this test. So let's enable it. And yeah, I think I rendered everything in the illumination buffer, and at the end I'm going to show it on the screen. So, well, it's applying the gamma, but it's okay. So let's see what happens. Because I'm deferred, I should be able to see it. And obviously, it's going to complain about many things. The first thing is that sprof doesn't have an sh property. How this class here has, it does has an sh property. Yeah. I'm not including the spherical harmonics, so he doesn't understand what's a spherical harmonic. Yep, sorry. I should include it where I'm using it. And I'm using it here, so it has to be here. Let's see if it likes it. Although it is complaining here, but no, it's not complaining. It works. Okay, so let's wait. I don't know, lately, the last month, every time I execute Visual Studio, any application I do in Visual Studio, it hangs the computer for like 10 seconds, like now it's happening, and then boom, then it starts. I don't know what's going on with Visual. But here we have a sphere, okay? Cool, so we have a way to visualize the sphere. We are on the right track. Couple of things. First, where is it? It's complaining a lot. I don't know. Visual intelligence is silly. 20 was too big, so let's make it a little bit smaller. And also, I want to send the data out with like the coefficients of the spherical harmonics. So I don't know on the slides how I call them, but yeah, here we have our code. So it's coefs, and I need the coefficients here. So if I have to go to the prof, to the sh, coefs here, okay? So in prof, sh, there's something called coefficients, if I recall correctly, but I need the first one. So if I type 0.v, if everything goes well, should find the first one. Because, I mean, a prof here has spherical harmonics, sh, it was called sh, no? In my code I was doing, yeah, sh, and this sh, it's of type spherical harmonics, and it's not getting it very well. And here, spherical is a struct that has inside a vector 3 of coefficients. Yep. And if I take the first coefficient and get the v is the direction of the first element of the vector 3, so that means I have the first element of these 9 values. Okay. So remember, when I do this kind of hacks of 0.0.f, it's something similar to doing something like this, the memory of the first element or something like that. But I can do this, I think. Yeah, because coef is a pointer, so I can pass the pointer to the first element, I think. Oh my gosh, that's bad. I did something very wrong, and I don't know where. This is why it's complaining. I did something wrong when I was coding. I removed a line or something. I don't know what I did, but now everything seems to be super broken. I included this file here. Let me check that this file doesn't have any problem. No. Okay. There's the error, like when you forgot to close one of the brackets or something that the compiler gets crazy. And yeah, it's doing this again. Oh, sorry. I think I forgot to put this. No, I forgot to put the namespace. I think it's getting bad because the names I'm using this is namespace here, and he doesn't know the namespace well, so it's crashing with something. And here I have this. I don't know. I think I should have put this scene thing on front of every single file. Because I think that the compiler is getting crazy that he doesn't know. Okay, not all of them has it. That is a bad practice. I should always put them in front of all the functions. And instead of putting it in front of all the functions, what I did was to put on at the beginning, say, hey, just use this namespace if you have any trouble. And that's bad because as far as I understand, if you do that, the compiler can get crazy. So let's remove this line and try again to see if it's luckier. And oh gosh, yes, this is good. Some of them are missing this function, and that's it. Okay, cool. Now we are back in business. So let's try with this. By the way, lately my computer has been doing a lot of weird things, and so if I suddenly disappear, it's just that my computer crashed, which happens like every 2 hours lately. So sorry, I will try to rejoin again, but could happen. Okay, so it works. I'm sending the coefficients, but I'm not using them. Remember, I need to use these coefficients on the shader if I want to have some sort of visualization. So in this shader, I'm going to receive the coefficients. Okay, so it's going to be something like this. Okay, so here, sorry, nine values. And now I need to read from these name values and render based on the normal. Okay, so, and always when you read the normal, always normalize it, otherwise you will have trouble. Okay, so how I transform all these coefficients and a normal into a color. You need to read from these spherical values, but because they are encoded as harmonics, doesn't make any sense to just read them directly. So the only thing I can do is I need to find a function to do that. And luckily, I gave you this function not long ago. I think, let's see if I have it around here. No, where I put it, no. No. It was at the very beginning, I think. Here. Yes, this one. Let's copy it. So a lot of trigonometry in this function, obviously. So let's put it, I don't know, here. So you can see this function. You pass a normal, you pass the 9 colors, and it's going to sample and give you a vector 3. Okay, so this is more like it's similar to texture cube, the function where we use to fetch from a cube map, but instead of you passing a cube map, you pass 9 colors. Okay, and here is the function that uses to compute based on the direction of the vector, assuming that the vector is normalized always. Is going to know the coefficients for every color and every direction. Okay. The only thing here is that this function expects an object called sh9 color, but here we have a here, this one, or here. So we need to convert our 9 coefficients to this one. So here we have 9 coefficients, but we need to have this sh. So I need to convert these 9 numbers to this sh. Let's call it once again here c. You see that this struct has a vector 3c. So something like this equals to ucoefs 0. Okay, I know it's ugly, and maybe there's better ways. And I can do it like with a 4. It's okay because it's going to unroll it, so then I don't have to do it manually. I mean, if we were in C, there's function to copy, like make a memory copy, but in shaders you don't have memory copy, so you have to do it manually. So now I have this object created sh, and all the coefficients are set on this object. So now I can call this function here. Okay, and I have to pass first the direction where I want to fetch, in this case the normal, and second the coefficients, in this case this sh. And it's going to return a color. So this is going to be the color we are going to render. Okay, so if everything goes well, what I should have now is a sphere that looks red. Remember the coefficients, I put the first coefficient to red. Okay, if the first coefficient is red, remember that the first coefficient on a transform, Fourier transform is just an offset to all the values, all the samples. So we are raising all the values to red. Okay, cool. But what about the other coefficients? Let's try to visualize what happens if we change the coefficients. So instead of changing the first one, let's change the second one. Okay, let's put a red on the second one. Remember that the first one is the global one, the second one is going to be half of the sphere. Okay, so let's see if it matches what we expected. And go, computer, go. Okay, there we have it. The first half of the sphere, okay, the top half. If I recall correctly, the top half of the sphere is red, but the bottom half of the sphere is negative red. But the problem is because negative colors are clamped to 0, we don't see it. But this area here is negative red. And I can show it to you if I go to the shader here and I say that instead of using this color, use the absolute value of the color. So if it's negative, make it positive, you will see that it also shines. Okay, so that's how the spherical harmonics work. Remember that it uses like a sinusoid, and sinusoids have positive part and negative part on the lobes, and so the first half lobe is positive, the second half lobe is negative. So when you put a coefficient, you're multiplying the coefficient, in this case red, by the positive in one area and by the negative in the other area. Okay, and that's not an error. I mean, that's how this system works. The thing is that you can compensate this if the first coefficient, the 0, is higher, then you can move everything out of the negative part. So that's why when you compute the spherical harmonics, it's going to be handled automatically. You don't have to do it manually. But so you understand. So it's always important when you compute this, at least to clamp it. Okay, so be sure that what you are using as a color is not smaller than 0. Okay, so here when you do a max, this is like clamping, but when you know that the values cannot be like clamping only below 0. So you say max 0 and something. If something is more than 0, max will say that 0 is bigger. So that way you always are going to get the negative out. Okay, because we want the negative out, because otherwise, if it could happen sometimes that when you compute the spherical harmonics, there's some negative value, and you introduce negative color, then you're going to subtract color on the pixels, which doesn't make any sense. So be careful with that thing. Okay, so we have this coefficient, and as I said, I can change to other coefficients if I wanted to. I don't know, the second one is going to be the front and back, the third one is going to be left or right, or something like that, and the fourth one is the strange ones because there are corners of the sphere. So let's see. So now we have a way to visualize this proof. Okay, now we have to find a way to compute what's inside these coefficients here, and we have to fill it with values that make sense. But for that, we need to capture amount of light we have on the scene. Okay, so here you see, as I was showing you, this is the coefficients of the fourth value. So this half here and this half over here, and there's another one for the half and the other half and stuff like that. Okay, cool. But for now, let's remove it, and we need to a function. So let's go to a renderer, and behind here we have a function to capture prof. Okay, a function where we're going to pass a prof, and it's going to be in charge of capturing the information. I'm going to put it before because it's something that you do prior to rendering the prof. You have to capture it. So let's go here, and this function is going to be a function that we're going to say, okay, I want to know how much light this point is going to receive from all directions. Okay, so there's only one way to do that. We have to make 6 renders in 6 different directions and take all the information and store it in some sort of image. When you render images, they are on the GPU, but you want to read the amount of light in every pixel, so they have to be transferred back to the CPU, and there we can do the computation. Okay, there are solutions to do this only on the GPU, so it's way faster, but I don't know. I mean, it will be much more complicated to do this algorithm inside the GPU, so we're doing it in the CPU. So let's go back to the slides and see how we can capture at least one. Okay. So this is how to render one prof, nothing important here. So here, we have to render the 6 directions and to get the images. So let's check this code and to see what we have here. Okay, so first we need a camera because we have to render 6 times. It's going to be a one-time camera. I don't need to use some existing camera. Remember that this camera doesn't have anything to do with the camera we are rendering the scene on. I mean, this camera is the camera we are going to use temporarily to do the capture of the illumination. And as I said yesterday, the camera has to have a fob of 90 degrees because it has to, I mean, obviously it has to capture a quarter of the scene if you see it from the top. So 360 divided by 4 is 90. About the near and the far, these values, I'm going to set them like 0 to 1 near and 1000 the far. I don't know, depends on the scene. Maybe you want to have it bigger, or maybe you want to use the far from other place, like from the camera, the global camera. I don't know. For now, I'm going to hard code it. And obviously the aspect ratio has to be 1 because I'm going to capture squares. Every side of this is a square, so the aspect ratio, the width divided by the height, is 1. So it's going to be, this is the perspective. Okay, so we have a camera now. Next step should be, okay, we're going to render 6 faces. Okay, again, sorry, I have all the vector 3s from the previous one, so let's put it like this. Oops, because otherwise some of you will not understand. Or I can add an F. I mean, if I put it an F here, it will be the same, but I think it's better that I rename it to vec3 also because I think it looks better. Okay, so let's go back to the code. Let's do it like this. Okay, so also an interesting thing. There's 6 images here. Okay, this class image is the same class that you use in computer graphics to load images, but it's made that it's the T-image. T-image is a class to store images. Okay, but you can specify if you want to use uint8 as for every pixel or a float for every pixel. I'm going to use a float, obviously, because I want to store as much light as possible. Okay, so it's an image where every color channel it's a float. Okay, so hence the name float image. Okay, so we have to render 6 times. Next thing is, where has to be the camera situated on the 6th time? Well, in the center of the prof. Okay, so the prof position makes sense. Next, which is the front vector for every of the 6 faces? This is important that it has to be go in the right order. Otherwise, my computation, when I expect that the second face has to be the one on the right, the third face has to be the one on the left, something like that, won't match. So that's why I have this class here that says, okay, if you're going to go for the second one, there are 6. The second one, so this one, is the negative x. So negative x means that the camera has to be pointed on the negative axis, okay, on the x axis. Okay, so I know the front. So how we build the center? Remember that the camera has to be specified by where is the camera and where it's pointing at. So it's I plus center. Sorry, I plus front. So let's go here and say that the center of the camera is position plus front. And the up vector, I get it from this struct also. This struct contains also the up vector here. The up vector is mostly always 0.010, but in some cases it's not, so that's why I have it here. Okay, cool. So I do a lookat. That means that the camera is going to be pointing in this direction I set up here, and now I enable it, so if any function in my engine reads the current camera, it's going to read it from here, not from the other one. Okay. Next thing, I'm going to render this image in a FBO, so I need an FBO, which I don't have here. So a couple of things. First, we're going to have an FBO here because I'm going to need it. Okay. So maybe I can define it here, maybe. So let's go here and say, hey, if we don't have the FBO for the profs, I need it. So I'm going to make a new FBO. And this FBO, I'm going to create create texture of which size, and this is the size that we were discussing the other day. I mean, I have to render a lot of times to capture the illumination. If I make this FBO big, every render will take more time, but the quality will be better because there will be more illumination from different angles. So let's go with 64 by 64. I think it's a good number. You can play around with it to see if the different numbers give you better results. Then how many colors? I only need 3 colors. Sorry, how many textures? 1, because I only need to control 1. And every texture is going to be RGB because we don't care about alpha. In this case, we're going to render an amount of illumination. But here's important. What's the type of every pixel? Here I'm going to say it has to be float. Okay. Otherwise, if I didn't say it's float, I will be losing a lot of information. Okay. So cool. We have FBO. Then here we bind the FBO. We have to render the full scene, and then we have to unbind the FBO. Okay. So now we will have the amount of light of that space. Remember, this we have to do this 6 times. So one phase we have the information. Once we have the information, we will call this function from texture. And this is a function where you just pass a texture here, and it's going to fill this image with the information from the GPU. This function, you can see it, maybe sometimes it's good to see these functions. What it does is called, where is it? Well, it allocates memory for the image, and get text image, this function on the GPU allows to read back pixels from the GPU, okay? So I can read the pixels back from the GPU to the CPU. The only problem here is I need to call this render scene forward function, which I don't know if I have a function to call it like that. Render forward. I do have a function to call it like that. So render forward is called. Okay. And so I don't know. Let's see in prefabs. I'm going to remove it. So maybe this is very old school. I'm going to remove this because I think last year we were having different structure. Let's call it render forward because that's the way I was calling it on the rest of the code. Okay, cool. So I have here now, if everything goes well, inside this FBO, I should have the scene. Let's check here, by the way, I call this render forward. What it's going to do, it's going to enable the camera, it's going to clean everything, then it's going to render the skybox, if there's a skybox, and it's going to start rendering the scene nodes. The only problem here I see is that when it's going to render the scene nodes, it's going to call render node, and render node here is going to check off the render mode. This is a little bit ugly because I'm using this function render node from the ferret and from forward. That means that if I'm not careful, it's going to enter here and choose, I don't know, the ferret, maybe because I was using the ferret, and I want to use forward now because when I want to capture the light, if I use the ferret, it will mean that I have to create a G buffer of 64 by 64, and I don't know. You can do it if you have a clean code. You can create the G buffers of 64 by 64 and call the function the ferret. But because I don't have that, maybe instead of using this render node here, I'm going to do something that makes more sense for me, like call it render mode. Sorry, I think will make more sense. Mode. Let's call it like this. So instead of using render mode, I'm going to call this function mode. So I'm going to add this in my when I call render node. You don't have to do this. I mean, you have your code clean, you don't have to, but I don't have it clean. I don't have all the render instances separated, render calls and all the things. So I don't want this function assumes that the render mode has to be the one it's enabled. I want this function to be more agnostic. So that means that any function that calls this render node has to specify how he wants to do it. So when I call here render node, if I'm inside, okay, I have to here to pass the same mode again, obviously. But what I mean is that here, when I call this render scene nodes, I also want here to have the render mode. So render mode. So I'm going to pass it here. Okay, and render scene nodes. Where is it? This function here. I have to specify render mode, the mode. Okay, and I do this because now when I hear rendering a frame, this rendered frame is going to call the ferret or forward depending on the mode. But this function here, once they start, if they're going to render anything, they have to specify the mode. And in this case, render mode is the ferret. And in the other one, function, in this forward function, render mode, sorry, no, forward, not the ferret. And in the other one, what is it here, the ferret one, when I call this function, it has to be the ferret. Okay, so now this is more agnostic. I have made this function agnostic in the sense that this function now doesn't know which mode do you want to use. But as I said, you don't have to do this, because if your code is well written, you have render calls and you have a function to render the calls. You can render forward that doesn't crawl the scene. So this is because my code here is very crappy. So anyway, so let's go back again to my render prof, compute prof function that I was doing before. So I render forward. If I call this function, it's going to render the scene. It doesn't do anything else. It's just going to clear the scene, render the skybox, and render the nodes in forward. Perfect, nothing to worry about. And finally, is going to read the image and put it on this array. Okay. At the end of these 6 iterations, I will have the 6 faces of the cube that matches the directions. And then I can do 2 things. I can try to upload this as a cube map and visualize it if I want to, which we will do next week, that for fractions. But for now, just compute the spherical harmonics. So this function, compute sh, you pass 6 images. Okay, you can see here it's going to iterate the 6 images, and it's going to read every single pixel. And when reading every pixel, it's going to compute the amount of illumination, and it's going to store the illumination on the coefficients here. Okay, and at the end you will have these coefficients that is going to be returned, and it could be, if you here it's I don't remember why it does this, but I think it normalizes some weights. Okay, so if everything goes well, at the end of this compute sh, I have the prof coefficients. So last thing we need to do is capture the prof, because we don't have to do this every frame. If we do this, that will be super slow. Let's do something. Let's go to my editor, maybe, yeah, and have here something like I can put a button here, but this is super dangerous. Well, I'm going to do it anyway. Oops. It's dangerous. Does anybody understand why it's dangerous to call this function from here? If I press the button, call the function. No ideas why calling this capture function prof from this function show UI can be dangerous. Any possible ideas? It's always good to think when you execute something, always think when you're executing that thing, in which moment of the execution flow. Because if you just call a function, oh, I call it from here, and you are in the wrong moment, bad things can happen. Because we can click the button many times, one after the other. No, I mean, you can click it. If you want to recapture it, it's good. I mean, we're going to click it many times. The problem is not that you're going to click it many times. The problem is when are you going to click it? If I click this button, it's going to call this function. Okay, so right when I click the button, it's going to enter this function, and this function is the function is going to do all the things to compute the illumination. The problem is that when I click this, when I'm executing these lines here, this is during the rendering. So while I'm rendering the scene, I'm going to render another scene, and that could lead to strange situations. So let's try it. It's not good, but I don't think it will break or anything. But be careful when you call a function during the rendering, because during the rendering you do another render, maybe the state won't be the right state. Okay, so I don't know. We will see what happens. If it doesn't work, I will put here a flag that says you have to update it, and I will update it at the beginning of the frame, but before I start rendering anything. That will be much safer, probably. So we have the prof, very dark. All the values are, as we said, are zeros, so dark. But we have these update profs, and if we click it, boom, we have something here, and it looks nice. It looks super nice. Look, it's there's light below, and there is darkest from the top. Okay, so I will say that it looks like something. And here there's some area, I don't know if you can see, but there's a little bit of yellowish on this area, which probably is this point here. I didn't tell you, but this point that you see on the background on the skybox, this skybox is, by the way, it's high dynamic range. It's like floats. And most of the colors are just between 0 and 1. But these dots you see here, this dot here, and this dot here, and there's another one here. This dot here, they are super bright. Like if everything is between 0 and 1, these are between 0 and 100. And what happens is that when you don't see it because it's clamping to the maximum value of the screen, so you don't see it. But if you multiply the skybox by, I don't know, I can do it so you can see it. If I go to the Atlas skybox function here, and I take this color, this is the color from the skybox, and I multiply by 0.01, and I reload this, see that there is still values. Okay, there's still light there, and there's still light here. So that means that it's beyond 100, because otherwise, if it was a little below, but multiplied by 0.1, you want 0.01, you wouldn't see anything. So super bright. By the way, this value, in the engine encoding, I have it like a parameter, so you can control how much light you want from the skybox. So that means that when the sphere has to read the color here, and there's a tiny amount of brightness that comes from that point over here. Okay, and we can exaggerate it if we wanted to. Yeah, let's do it. I mean, why not? So I'm going to multiply this by skybox intensity. Okay, so I'm going to have here a uniform skybox intensity, and this skybox intensity should come from the scene. I mean, if the scene contains information about the skybox, which does here, the scene has this is the skybox file name. It should also contain the skybox intensity. Okay, and by default is going to be 1. So skybox intensity is going to be 1. But when you render the skybox here, render skybox in this function, maybe you can pass here the intensity. So the scene, I don't have the scene here. Yeah, scene is there. The scene, because the function render skybox doesn't support any parameter. Sorry. Plot intensity, and I'm going to pass to the shaders. So shaders set uniform. Skybox intensity is going to be intensity. Okay. So now when I call this function render skybox, I'm going to pass here the scene skybox intensity. Why doesn't like it? Because I didn't modify it on the header. 1 second. This is on the renderer. Render skybox float intensity. Okay. So now I only need to have a way to control it, because I'm going to put it on the editor here. When I specify the skybox here, I also going to have here like a ingui drag float. I think it's called float, and it's going to be skybox intensity. So I'm going to go to the scene, the skybox intensity, and it's going to be this. The first value is the speed, so let's go with this one. And this has to be an address because this function has to be able to modify it. Okay, so now we can control this intensity. Let's see if I can test it now. I forgot something. Yep. Intensity. No, instance, no. Skybox intensity. Yeah. Okay. It's good to have control over any parameter on your scene, not only from the rendering point of view, also from, I mean, when maybe an artist creates a skybox and he says, oh, this skybox is very bright, I want to reduce it. So now we gave him some control over that. So let's see. Okay, we have the same, but if I go here, we have this skybox intensity and I can play around with it. Okay, so it's interesting because if I put it very bright and I compute the probes again, you can see how there is more light now because all this light from the skybox it's captured with the 6 cameras, and when I make display harmonics, and if I put this very low, not negative, no, but very low, and I delete it, all that information is gone. Okay, so yeah, this is capturing the amount of light. Other thing I can do to show it to you is this sphere is capturing the light also from this wall over here. So, and this wall is illuminated by this spotlight. So if I go to the spotlight now, and I say, hey, super intense, okay? If I capture now, the right side should be very bright, but the left should stay the same. So if I do it now, boom, you can see, yeah, this area is bright because the floor is also bright, but this is still dark, okay? So it looks like this is capturing the illumination of the scene using my 6 renders. By the way, the amount of time it takes to make the 6 render, I don't know. I mean, obviously when I press this button, it's very fast. But, if I have to do this for lots of spheres, it's going to be slow, okay? So always it's good to have very optimized for this kind of situations. Okay, so we have done the more complex part. Now we need to do this for all the points on the scene. So that's why I say that here it makes more sense to create an entity called Irradiance cache, where you can move it with the editor, and where you can specify where are the number of spheres that you want to have, the props, all those things that we were doing with Blend the other day. I don't have time for that. It's only half an hour and I want to finish. So I'm going to hard code a lot of things. So always feel free to play around with the editor and make new entities and try to see how they work, because I think it would be super interesting. So in my implementation here on the slides, we're going to make a regular grid. Regular grid doesn't mean that the distance between the bolts has to be on X, Y, and Z the same. It could be different, but at least the importance is that all the spheres on one axis, they are all at the same distance from each other. Okay, so it's a regular grid. So here there's a code. I'm going to construct a grid. So first, we are not going to have one probe. We are going to have a lot of them. So we no longer want to have a probe. We want to have a vector of probes, okay? Because we want to have lots of them. So this no longer applies. And we want to have a function to define where are the probes. So let's put it here. I don't know. I don't know if it makes sense to, I don't know. Capture Irradiance. I'm going to do it like this. I don't know if it's the best way, but let's go with this. So this function, which doesn't exist yet, so let's going to put it with the probes thingies here. Okay, as I said, the right way should be that this function should receive some entity and use that entity as a way to know where are the probes. I'm going to hard code, so it's going to be ugly. Back 3. So you can see there's some numbers here hard coded. I remember these numbers work for this scene I'm showing you. So what are these numbers? Okay, first number says the position where the grid starts, and the second number is where the grid ends. Maybe I can make it a little bit better. No, I don't have time. If I do it, I want to do it right way, but if I do it the right way, it will take more time, and I will have time to show you other things. So, so what I wanted to do is, I don't know, pass some entity here and use the model to define where are these probes on local space from the model, so I can rotate these spheres. It can be done, but well, anyway, let's do it like this if I have time. So this is where the probes start. So you understand, if I have all these probes, okay, imagine that the grid is like this, okay, something like this. Prof start pose is the position of this prof here. Prof end pose is the position of this one here, okay. Dims is the amount of probes we have. So dims here is 4, and in this axis is 3, and on the Z axis, obviously. And also, if you subtract end pose and start pose, you get this vector that goes from start to end, which is this one here. And using this and divided by the number of elements, you know the distance between this one and this one, and this one and this one, and this one and the other one on the top. Okay, so this is the deltas. So now we have constructed a grid. Okay, now it will be nice that for every element on this grid, by the way, here it says probes here. Okay, well, it's constructed here, the probes. I put it here. Yeah, I don't know. I don't want to have it here. I will put it outside to go faster. So now I have all the probes positioned on the scene. Okay, maybe it would be nice now to visualize these probes so I can see them on the screen. I didn't say how many probes do I have, so I'm going to allocate here the data. So what I'm going to do here, here, there's probably a code on the slides about this, so I don't want to go faster than the code here. So this is more the code that set up it iterates for every dimension. So it's going to iterate like here, 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 and then here, 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 and here, here, here. And for every iteration it does, it creates one prof, it sets up the coordinates and the dimension. Don't worry about these things, like the 3. And it sets up the position based on, from the start position, delta multiplied by the XYZ. So if it's this one here, it's going to be this vector here multiplied by 3 to the right and 3 to the bottom. Okay, don't worry. It just constructs the position of this grid, okay, in a very simple, basic way. Every time I create a new prof, I put it back on my prof list. Here it will be important, always be careful, because we are doing this every frame. Always be sure to clear the content. Sorry, we're not doing this every frame. We're doing it when we want to recompute all the profs. But because this is pushing back, maybe it's always better to do something like this. Yeah, I'm going to do a little bit more clean. So it's going to be, how many profs do we have to have? It's dim x multiplied by dim y multiplied by dim z. Okay, so and instead of using profs push back, which is very slow, I'm going to use the index, p index. Okay, so that means that we only allocate memory once, and then we put them on the right spot on this array instead of pushing back at the end of the array, because when you push back, it has to reallocate all the memory, and that's super slow. Okay, so now we have all the profs created here, and because we have the render prof function, remember, well, maybe we can extend it. So and say, hey, I want to render all my profs. So I'm going to render from all my profs, okay? Assuming there is not a while loop. No, there's not a while loop. So I'm going to go to the profs and take the while prof and render it, okay? So at least now, if I want to see if my profs look good, at least the distribution of them, sorry, here they have the capture prof, which, sorry, was how did I call the function? Capture Irradiance. So if you press this button, it's going to call this capture Irradiance. So now we have a way, and proof resize is clearing the vector. Proof resize, what it tries to do is it checks how much memory an array has, and if it needs more memory, it has to reallocate another place on memory. If it requires less, well, it can decide. And if you resize with the same size, it doesn't do anything because he knows. But it's not going to destroy, well, it's going to move memory around, but it's not going to initialize anything or clearing it to 0 or anything like that, okay? It's more like it's going to copy the current state to the new state always. So you're going to try to maintain the same state. So here, we don't see anything because we don't have any prof, okay? But if I go here and click this button, I should have all the profs here. Okay, the problem is they are all here, seems to. What's going on? Okay, something didn't work. Let's check again, 1 second. So we call this function compute irradiance. Oh yes. I'm silly. I just put this and even put nothing. Also, you want to skip saving this array, you can do this. You can say there is a reference to this one. This is a trick to speed up some computations. When you do this, you mean you know there's memory for this element. So you're telling the compiler, because I know there's an element here. This function, when you call an STD vector and you pass the brackets to go to access value, it doesn't return a copy. It returns a reference. So you keep the reference. That means that this variable p is exactly the same in memory as this position on the array. So if you modify this p, you're modifying the array. But this only works because you have the answer here. If you remove this p is a copy, not a reference. So let's put it like this so I don't lose it. So let's go again. And let's see if it works. Yep. And I click here and it crashed. Okay. Blank. I think I'll read out of memory. Damn it, I did something very wrong when I was reading the profs here. 1 second. Ah, yes, I'm super stupid. Yeah, I'm stupid. I cannot do this because I'm reading p index, but p is p. So sorry, it doesn't make any sense. Okay, this is better. It's not so fast, but it's better. I don't know if you saw, but I was reading p index, What I should have done is take this value here, which is the index, and put it out before and use this value as to read. Anyway, I try to optimize sometimes so much that I break things very easily. So as I said, now I go here, click update proof, and boom, we have proofs everywhere, okay? But they're black. They're black because we didn't compute the amount of illumination for all the proofs, okay? So next step should be, can we compute for every one of them how much light does it has? Well, yes, we can do it, but we'll be prepared. This is going to be slow. So let's go to the, here it says, maybe you want to compute the coefficients for every prof. So yes, we can do this. I'm going to iterate through every prof we have. I can do it like this, or I can do it like here, directly prof size. Okay, and I'm going to take the prof from the end position. So now I can do the thing I was saying before. I can say this is profs of IP. I don't want to reuse the same sometimes the same iterator. So I have here the prof. Time to compute it. So compute prof, or a capture prof, and here I pass the P. So everything goes well. I should have all the profs captured here. Okay. So be ready to do something small, slow, because computing 6 renders for the amount of how many profs do I have now? I think it was 10 by 10 is 100 for 400 pros by 6 faces. That's 20,400 renders. But also remember, I have to transfer the texture from the GPU to the CPU and do the compute the display harmonics. That's a lot of work, but we can try it. So 1, 2, 3, and it hangs the application. Doesn't do anything. I don't know if it's recording OBS, but boom, we have all the props here. Okay. Be careful if you click the button now. Well, it wouldn't happen, but one error I've seen some people do usually is that we are rendering the profs. So render profs. So we have this function here to render the profs, but we're calling this function when we're computing the Ferrer renderer. So be careful if you use the Ferrer render to compute the profs, because what you're going to end up is with some sort of recursive situation. So when you are computing the amount of light the profs have, because you're rendering the prof, maybe you're in the book mode and you want to render them, you are also render the profs inside the amount of light that the profs can see. In other words, profs are seeing other profs, and that's weird. So always it's good to say here something like show profs, and by default this show profs is going to be false, so I don't want to see the profs unless I want to. So here show, and what's important is that when you capture the irradiance, be sure always before you start capturing to set up this to false. Otherwise, maybe the function that is going to capture the amount of illumination is going to see a lot of spheres and it's going to compute it with the spheres around. Okay, if you want to do it right, you can save the current state and at the end you can put it back. Okay, so now, and by the way, I forgot to put on the UI always these kind of things, otherwise you won't be able to edit them. Cool. So now I have half of it. I have profs. He doesn't like it because this is an execution. Sorry. Okay, so now I can show the profs. Okay, and we have still 20 minutes until the end of the class. Okay, capturing the profs takes time, as I said, because depending on the number of props and the complexity of the scene, the number of elements, it will take more or less time. So I'm going to capture it now. So while it's capturing, and I hope OBS is not dying now when doing this, I will have at the end of this call of the function, I have all the props computed. You can see it here. Okay, and we can try to see if they look right. For instance, this sphere here has some reddish here. It's good signal because this is close to here. This here, for instance, oh, God, almost I want this area to be close to 1 so you can see the emissive color, but it's okay. And here you can see that this one is close to the wall, so you can see the amount of light here. So, I mean, they look quite nice. I mean, they match. The important always that they match. That what you see on the spheres matches your scene. Like, for instance, I don't know, imagine I take this trash bin, I'm going to put it here, okay? And I'm going to go to the material, which I can go here, trash bin, and I'll search here on the material. And I don't know, cap body here. I think this is the big one. And I'm going to say that it's emissive, so it's going to shine, okay? And I'm going to make it shine a lot. So I can do that because remember that if I go here to the values of emissive and I right click here and say from 0 to 1, I can modify these values and say it's like 10. I'm going to put 10 only on the red one, but not on the other one. So this is going to be super red and white on the other ones. And you don't see it super red, but this is ultra mega red now. And it's nice because if I go now and update the profs, they should catch it. They should catch a lot of red coming from this object. So let's see if it matches. Something weird happened. Ah, yes, because the renders are not shown. And boom, it's true. You can see how this object is emitting a lot of light and is captured by all these profs here. Okay, cool. Even you can see that even far away ones, like these ones, they are still capturing a little bit of this. Okay, cool. Because capturing all the props takes a lot of time, I would recommend you to do something that is very easy to do. I'm going to do it because it's only 3 lines and it can save you a lot of time when you're debugging this application, which is if you have to pre-compute something, don't pre-compute it every time because that will take a lot of time. Pre-compute it once and store it on hard drive. We have a hard drive, that's nice. So how can we do that? Every time we capture the irradiance, okay, at the end, maybe I recommend, if you have time, to save the information about the profs on a file. So you can do it very easily if you go here and say, I want to write, I think I have a function write file on my engine. Yeah, only for, let me see, I have a function to, I mean, you can use the write functions like regular people do, but I think I put in my engine some functions when I want to read files binary. I didn't put the one for binaries for writing. It's okay, it's easy to do. So you just have to do these kind of things. Let's do it. So what I'm going to do now is save the content of the std vector with all the profs. So what I have to do first, I need to have a file name. So let's call it irradiance cache.bin. And I'm going to serve, it's a binary file, so you have the WB. And if there's no error, open the file, because if there's an error, there's nothing to do. But if there is no error, I'm going to write down the content. So first, you have to specify the pointer to the first element of the data that you want to send to the hard drive. In this case, if I go to profs, to the first element, and I say the address of the first element, that obviously is going to be the pointer to the first one. Okay, cool. Next thing, you have to specify how many bytes. How many bytes? I know they are profs, this array contains a lot of profs, but I need to know how many of them. So in this case, if I go here to profs size, it will know that it has to take this, multiply it by this to know the amount of data I'm saving. And this is the pointer where I want to save it, and if close, it's going to close the file. So as simple as this, with 3 lines, I take all the chunk of memory and put it on the file. Okay. The problem if I do that is I won't know how many profs do I have. I will have a file with all the profs, but I'm not storing the amount of profs. If I have 1, 10, 20, 25. Okay. If I wanted to do it right, I should also before here store the amount of profs. I can do it now if you want to. So num profs, obviously this integer is this one here. So I'm going to store these numbers. So you go fbright. I'm going to store which thing. I want to read from this numprofs. Okay, the address of this value and how many bytes. Well, the size of an int. If you don't know, you can specify size of numprofs. In this case, because this is a basic type, it's an integer. It's like the same as saying the size of an integer. Okay, and how many? There's only one. Okay, so and where on the f file. Okay, so now I have stored 2 things. First, the number of profs, and then all the profs, the array that contains all the profs. Cool. So now if I wanted to read these profs again, I can do it very easily, like load irradiance cache. So you have to do the opposite. Okay, so how you do that? You go here. You are going to open the files, irradiance-cache.bin, for reading in binary. And by the way, I'm going to put this function on the renderer because I'm going to read it. Okay, I'm going to open the file, and then I need to read the number of profs. So I'm going to create this variable, but I'm going to do fread. I say, hey, I want to read, and I can even use this function here. I want to read in this direction here, this amount of bytes from this file. So it's going to read from the file and put it here. And then I want to resize my profs using these num profs always. And now I'm going to read on this address and the first element of num profs, the amount of profs that says here, and close it. As you can see, it's almost the same code, just reverting the actions. Very important that after we have read the number of profs, we have resize it, because if we didn't resize it, when we read here, it will break. So yeah, I think it is enough. So sure, let's try it now. Execute the code. And fuck, I forgot to put the function. Well, yeah, I can still do it, but I didn't put a function to load it, but it's okay. It's going to work anyway. So I have here my code. I compute the profs. I wait until they are computed. Take some time. And then I show the profs, they are computed. And if everything goes well, I should have a nice new file somewhere here. Irradiance-cache.bin, cool. And it's not empty, it has 52 kilobytes. As you can see, an Irradiance cache doesn't take almost space because it's just a bunch of floats, like only, like, I don't know, 100, 200, 1,000 floats, which is not nothing. So I have the Irradiance cache. So as I say, I'm closing the application, so I have lost. But the good, nice thing is I can have a function to load the Irradiance cache. So let's put a key or something. Like, yeah, I'm going to use the same function I was using before. Here, of.profs, load profs, and it's going to load Irradiance cache. Okay, and if you want to look better, you can do this same line. So that means that it's going to put the both buttons on the same line on the editor, so they look better. And we have only 15 minutes to the end of the class. And I haven't computed the complex part. But anyway, so you can see if I show the profs, there's nothing here. But instead of clicking this button, I click this other one. Ta-da! My profs are back, and they don't take time. So even you can put this load profs at the beginning of your render function if you want to, so it's going to load them when you start the rendering, so you don't have to compute the profs every time you want to test something, otherwise that would be super annoying. Okay, cool. So last step, we need to pass this to the shader and compute it and render the amount of irradiance. Okay, so I'm going to make a shader now. Okay, so no, I'm going to start from, I prefer to start from the C++. So we have all this function, so let's go here and say, I don't know, apply irradiance. I don't know, a function that applies the irradiance. Okay, I'm going to call it from my render forward. So here, render forward is going to, yeah, no, sorry, the ferret, because forward is it's a crappy function. So here, from the ferret. So yeah, I compute the illumination buffer, blah, 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 all the things here, and at the end, okay, when I have computed the amount of light, I can do it. I mean, when I do the global here, I could do it here. So I compute the global. Yeah, I'm going to do it here. And then I add here the irradiance. Okay, here apply irradiance. So if everything goes well, it should add to the current buffer the amount of irradiant light. Okay, so let's make this function apply irradiance. So I'm going to put it below render prof, maybe. So this function, it has to render a full screen quad. Okay, so as always, mesh equals gfx mesh get quad. We're going to render a full screen quad, and we will need to reconstruct the wall position for every point based on the depth buffer. So I'm going to call it only now for the for the ferret, because we are going to need to reconstruct wall position, and you cannot do that from forward. I mean, I can do it on forward, but then I will have to do it during the rendering of the forward pass. So it makes more sense to do it in the ferret only. You only have to do it on the ferret, this algorithm. I don't ask you to do it on any other one. So I need all the G buffers and everything. So let's go with the classical thing of when I pass all the buffers, which is all this crappy code. I'm going to copy all this code because I'm going to need probably half of it. So the shell is going to be Irradiance. Irradiance. Okay. So I have a shader. I enable it. I need a camera. Always current camera. Okay. So if everything goes well, I will have the G buffers, color, depth, blah, 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 erase, blah, blah, blah. All these E points. This was from the other day. Nothing to do here. And here, this is mesh. Okay. I don't have to modify the depth test. So I don't read it or anything because I have it already. I do have to do blending. So I'm going to enable blending because I need to add this this quad to the amount of light I already have on the buffer, because it's going to add more light. This is the Irradiance light. Keep in mind that in the current render, we have the ambient, and this is already an ambient. So I would recommend you that if you use the Irradiance, you don't apply any ambient light because it's going to add more light to the scene. So you have the ambient and the Irradiance on top of that, and that's going to make everything too much bright. And so in these cases, when you have some kind of Irradiance cache, you remove the ambient. But anyway, so I'm going to make a full screen quad, and the function is going to be GL1 blah blah minus source alpha. Now I'm going to go for source alpha, just this one. Okay, because I want to add. Remember that this one, when you say GL1 here, it means that it's going to add on top of what we have already on the buffer. Okay, I enable the shader. I'm passing, but I need to pass here my profs. And remember that my profs are now a std vector. I cannot pass an std vector. Somebody could be tempted to try to pass something like a set uniform vector 3 array, as we did, with all the colors of the arrays. But the problem is that the uniforms has a very limited amount of space that you can use. In some devices, it's very, very low. That means if I try to pass now all the profs as a uniform, depends on the hardware, maybe it works, maybe it doesn't. So when you have a lot of data and you want to read it from the shader, there's two ways to do it. The first one, the more general one that we have been using for more than 20 years, is you put it inside a texture. So you create a texture, you put the data inside the texture, and then you enable that texture, and from the shader you have to read it. It's kind of annoying because reading from textures, I don't know, you have to find the UVs to go to the right pixel and disable any kind of interpolation. So it's annoying, but it can work. In this case, it makes sense because if you think about it, every prof is 9 colors. So it's very easy to understand that if every one prof is defined by 9 colors, okay? Remember the 9 coefficients. And I have, I don't know, 100 profs, then this is more or less a texture that is 9 pixels wide and num profs height, okay? So you can do this. You can put all the profs inside one texture, send it to the shader, and then when you know for one coordinate position, then you will have to understand in this position which is the row and go to that row, okay? So that's one way, using a texture. But there's other way, which I'm not going to explain because I don't have too much time, but it's supported by my engine, which is, I don't know if I added on, yes, this one, this buffer objects. This allows you to send arbitrary data to the shader, okay? So that means that you can create a block of data and you can pass it to the shader and you can read it on the shader like some sort of a struct. Okay, and this is not limited. SSBOs, is a scala, this kind of thing, can host until, I don't know, 128 megabytes. So it's super, super big. They are slower than the uniforms because when you access this data, you're not accessing a local cache of the shader. You have to access to the main data, the main RAM of the GPU, and that's slow. It's like accessing a texture, but you can do even operations. Even you can modify this memory from the shader. This is the possibility that a shader can write information inside this buffer, okay? But I don't want, using these buffers is also a feature that is supported only on OpenGL 4, not on OpenGL 3, and I try to keep my engine OpenGL 3 compliant, so it works in every computer. So let's go with the one of using textures. It would be nice to use the other one, but I think it will be more dangerous. So we have the profs. Next thing, upload to the GPU. So let's copy this code. We're going to read this code. It's not so complicated, you will see. So after I have captured or read I need to have here the profs, okay? But for that, I need to upload it. So previously, when we were here, we said we can load Irradiance or capture Irradiance. So I'm going to upload Irradiance cache. So this function is going to be the one that uploads the data to the GPU, okay? So after we have loaded, maybe here we can put our function upload cache. I'm going to put all this code. We will see what this is now. And when I load the Irradiance cache, I'm going to upload it. Very important. And when I generate it here, also I'm going to upload it. Okay? So remember, if I generate the Irradiance cache here, this is capturing every prof, I upload to the GPU, or if I load it from the file, I also upload to the GPU. So this function is going to require first that we create a texture to store all the profs. So I don't have this texture, so let's go up and create this texture here. I don't know, maybe it will be better to create it inside the renderer, but for now, let's go with this. Okay, so I'm going to create, you can see here, I'm created a texture. I'm going to delete, if there is another texture like this, I'm going to delete it. Okay, this is important always, like if I'm going to create a new texture to upload the Irradiance, first be sure if you already have a texture, delete it. Maybe I didn't need to delete it. Maybe I can reuse the previous texture if they have the same size, but I don't want to waste time checking and now do it. If you want to do it, it will be good. So this texture, as I said, is going to have 9 pixels wide because every row of the texture is going to be one prof. And as many profs, as many rows as profs. Okay, so 9 columns, prof size profs. Cool. It's going to be RGB because we don't care about alpha, and it's going to be floats. Okay. So now this being said, I need to find to allocate memory for all the spherical harmonics. You can see here that I need to do this. I need to know how many the dimensions of the. Yeah, I think I forgot about this. I need to know the dimensions of my array. So how many prof, there's an X and Y and Z, and I lose that information because I didn't store it on the file. So maybe I'm going to destroy this one because this Irradiance cache I created, it didn't have this information. And I'm going to create, when I store this information of the Irradiance cache, I only stored the num profs. I'm going to do something more interesting, which is this. First, I'm going to create something like, let's call it a struct here. Let's call it S Irradiance header. Okay, and I'm going to put here some data. Okay, so I'm going to put here num profs. And as I'm going to store here the dimensions, and I'm going to store here the position, the start, and I'm going to start here the end, and I think that was it. Yeah. So these are the information I'm going to need if in any moment I need to reconstruct again the data. I need this. Remember that when I was doing the function that created the capture Irradiance here, I hard coded these values and I never stored them anywhere. Because of that, I lose this information. And also here the delta, I didn't store it, but delta I don't think I need it. So it's important that I try to save this information. That's why I say that you have an entity, you can put this information inside the entity, but I don't have any entity, I'm hard coding everything. So let's do that. I'm going to take this struct here that says Irradiance cache info. Okay, so I'm going to put it here. Sorry, what is it's info. I'm going to put it on top of it here on the top. So I have this structure here, and because I have the props, I also got so info. Irradiance cache. Irradiance cache info. Okay, so I have some cache info, and by default it's going to be crappy values. Every time you create an struct, always it's good that everything is 0. And this vector3 always is set as 0, but this int is not going to be 0. So what I'm going to do here is be sure always that to say, I don't know, numprofs equals to 0, to be sure that there is no trash values there, and because you read that value is going to be trash. Okay, so now when I create the irradiance, so when I create the irradiance, I'm going to try to store all this information here when I'm going to store it. So I'm going to go here and say, hey, the dims are dims. The start is start. It's kind of here, no? It's like start post. Start post. Sorry, start post. The end is going to be end post. The dims, sorry, not dimensions, dim. And the number of props, which I don't need the number of props. The number of props is dim x, y, z multiplied by between each other, but I don't know. Okay, so now I have this structure that contains all the information I need. So that's easier because if I can go here to this bright, I can say I want to bright this one object, and this is the size. Okay, so and the number of props here is, I don't know, prop size. Okay, so now I have a tiny structure in memory that contains all this data. I store this one and then I read it back here. So here I'm going to say, instead of numprofs, I'm going to go and say read me the irradiance cache info from this place here, and now use these two numprofs and read the numprofs. So this is going to be the same here. Okay, cool, this is better. So now at least I don't lose the information about the irradiance cache, where it was created, everything. Okay, that's important because now I'm going to need that information here, the dims here. So let's, I don't know, go here and say vector3 dim is equal to this dim. Okay, dims, sorry. So I have this information, the same for the start and the end. Now I only need that information. Okay, cool. While I explain this, I'm going to recompute the irradiance cache because otherwise I won't have it. Let's go. So let's check this code. I'm creating the texture. I'm allocating memory to store oh, it's crashed the application. It crashed because, let me see, I used something somewhere that it shouldn't be being used. Let's see, because I didn't call any function new. So maybe I was calling my irradiance, my irradiance function. Yeah, I know what it is. I'm sorry, I didn't have to execute it. I'm calling the function to render the quad, but I didn't specify the shader. I didn't create the shader, and because there's no shader, that's null, and because it's null, I'm using a shader that's null, and it's crashing. So, yep, stop it. So the function here, irradiance, apply irradiance, this function, we should disable this until further notice. Okay. No, I'm in debug mode. Ooh. Stop it. Well, anyway, I have to wait now. And we are over time. Give me 10 more minutes. Sorry, but this is, I want to cover as many aspects as possible about this topic. So that's why I wanted to go deeper. So I wanted to execute it to capture the irradiance. And while it's doing that, I want to check this file here. So we are going to create a texture, okay? And we are going to fill the pixels using the props. And to do that, you don't have to create an image and put every pixel. You can just use the same amount of memory. So that's more or less what I'm going to do. First, I'm going to capture the irradiance here. So capture it. Always when you capture this, be sure that every texture has been loaded. Otherwise, you're going to be capturing scenes that don't have the right texture yet. So, okay, so we have the props here. Okay, they are saved. We can execute now, later, and load them. And just check to be sure that they are properly loaded. So go here, load them, show them, and everything goes well. Cool. Okay, so I create a texture. I create memory to store all the pixels. I'm transferring every spherical harmonics from every single prof to this data structure. What I'm doing is I'm repacking the data, no? Because what I had before is every prof, like when you see the memory of one single prof, there is a position, there is the index and something, and then there's the 8 coefficients, okay? Or the 9 coefficients, sorry. But I want to construct an image, so for that I want to take every one of these and put them together in one single row for every single. So I want to remove this area here. Okay, so to do so, the easiest way to do that is just to copy them to this memory now. And now I'm going to call this function upload on a texture and say, hey, I'm going to pass you some data uploaded as the pixels. So I'm going to say this data is a GLB, is 3 channels, they're floats. The third value is if you want to generate memaps. I don't want memaps, so don't generate them. That's why I say false. Generate the memaps, I will never use it, and also they're slow to generate. And here is the pointer to the first pixel. So this, from this address memory, go directly forward to get all the pixels. So if I do this, boom, I have all the pixels upload on the GPU. Okay. So I can check it. Finally, I delete all this data because I don't need it anymore. It's already in the GPU. And here I disable any kind of meme mapping with this texture. I don't want to use meme maps ever. Okay, so next step should be to visualize this texture to be sure that this texture works well. So I'm going to load the profs, and they are here. But I can visualize the texture if I go here, visual textures. If I go to the bottom, you should have a very weird texture, which is this one. Okay, so you can see these are the coefficients of all the profs, and you can see that the first pixel, this is 9 pixels wide. The first pixel has a lot of information, which you can see that the tones here, the colors match a lot the scene, and there's some tiny variation. You can see this yellowish thing, which is the light that comes from the skybox probably, and I can see that this is it. If I go to the skybox, as I was doing before, and increase the intensity of the skybox, if I go here back and update the profs, you will see how, let's go, boom. You can see now that, well, it's very bright, but you can see that the coefficients, they have more information now. Okay, cool. So I have a texture, I have all my data. Last step, read this data from my GPU and use it. So this is the shader. So let's go to my function that I was doing before, apply Irradiance. And I now have a texture, so I have to upload. I'm going to upload. I have to upload a lot of information here. So let's go to the slides because it's going to go faster. I need where it started, where it finished, the wall position, blah blah blah, all these things. So I'm going to have to pass it to the shader. So the start, the end, and the dimensions you can see. So I'm going to have to set uniform. I'm going to try to keep the same name as on the shader. So here are start. This is where it starts. So Irradiance cache info dot start, the end, and the dimensions, and finally the more important one, the texture. Let's call it, I don't know how I call it on the slides. Let me see. It's called prof texture. So prof texture, and here the texture is going to be in a slot. This is 1 and 2. Also, I'm not passing the albedo texture. I'm going to pass also the albedo and the albedo texture, because I'm going to need the albedo texture. And I also will need probably the emissive one, but for now, let's go with only the albedo texture. I need albedo texture because for applying the illumination, I need to multiply by albedo. So I need albedo. So this white texture is, if there is no, yes, there's albedo texture. No, I think I call it normal texture, albedo texture. Yeah, I did it right. So by the way, this is albedo texture. I was using it wrong. Yep. Okay, so in the 0 goes albedo, and 1 goes the normal, and 3 goes the depth, and this one gonna go on the 4th. So it's going to be Proves texture. Okay, so I think I have all the information I need to reconstruct the position and to read from the profs, and yeah, So let's do it. This Irradiance shader, which is the last step on my long chain. So here is going to be Irradiance, and it's going to be a quad, because this is going to be a full screen quad, and this Irradiance FS. I'm going to go to the sphere gloves here, because this one has all the things I need to read from the coefficients. So I'm going to use this Irradiance.fs. I think it was called like this. Yeah. Okay. So I'm going to need this code here, all this compute, blah, 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 blah. So I'm going to copy it here. Indeed, I can, yeah, I'm going to start from here. Okay, I'm going to need to reconstruct the position, so the wall position from the depth texture. Sorry, I don't remember. Here, this is an example of a function that reconstructs the wall position from the albedo and the normal and everything. So this is a good example. So I'm going to go here, and I'm going to need 1 second. Spherical prof. It's here. I'm going to put it below. I need here, and I'm going to move this part here to the top. Yep. Okay, I forgot the line that says the version. Yeah, this is an important line. Otherwise, the compiler won't work. Or where is it? Yep, here. Okay, so we have the 4 buffers. Oh, by the way, this is not being used, so I don't need it here. Ambient light, I don't need it. The construct, blah, blah, blah. And I need these parameters I was passing before, this RR start, blah, blah, blah. So let's copy these ones over here. So I'm going to go from here to here. So it's going to be uniform vec3. Okay, oops. Okay, and the texture. I don't think I passed the props texture. No. So it's props texture. Oops. Okay. I have everything. So and all the things about reconstructing the wall position. Yeah, I forgot those ones. The UVP and the URES. These 2 ones. Okay. So depth. I need to use the VP to reconstruct the wall position. So let's search for a shader where I do that. Here. So I have an example here where I construct the wall position, and I reconstruct the normal too. I'm going to use this one here. Like this. Better. Okay. So here I have, I read, by the way, the IRRES is sent by the other one. Yes, okay. And using here this is FBO. Whoa, no, don't use that one. Use this width and this height. Okay, I was using some random things. Okay. So get the depth, reconstruct the set, the wall position, read the albedo, the normal, normalize the normal. So I'm ready to do here my magic. So now, what's the algorithm about? The algorithm we're going to do is we have a lot of profs on this regular grid. This grid, by the way, is always axis aligned, so you cannot rotate this grid now because we don't have a model, although it can be used. I will put the slides about it. So given any position on the wall space, I need to know which is the closest prof to I mean, the right thing would be to find the 8 ones and do the trinomial interpolation. I don't have time to do that now, but what I'm going to do is I'm going to find the closest one. Okay, how can I do that? What I'm going to do is first convert this wall position to a local position where the 0, 0 is here. This is the 0, 0. Okay, which is very easy because this is the start and this is the wall position. If you have wall position, you subtract the start. You are in this space where the 0, 0 is the first one. Okay. Then what I'm going to do is I'm going to divide this position by the distance from here to here, okay, which I know it's end minus start, okay. So that will be like a value, with this position will be a value between 0 and 1, being 0 here, being 1 here. So in this case, the x will be probably close to 0.6 or something. And then I'm going to multiply this value by the number of elements. In this case, there's 3. So it's going to be multiplied by the dimensions on x and y and z. So this will be something like, if I multiply this by this is 3 in this example, 0 by 3, it will be 2 dot, I don't know, 1 or something like that. I don't know. So that means that if I round this number, it's going to be the number 2. So I know this is the number 2, the closer to, and I do this for every axis. Okay, so it's a very simple way. There's another better way where you use the inverse of the model matrix, but I don't want to waste time on that one because I don't have time now. So you can see here on the example that what it's doing here, improve interpolation. No, this is here, this code here. So I'm going to copy this code, and you will see I put it here. So let's go again by this code to see. I'm taking the, as I said, the start and the end. I subtracted, I get the range, and then I got the wall position, which is wall pos. I'm going to call it wall pos to be sure that it doesn't have to change many times. And I'm going to subtract the values. I'm going to push it some through distance forward. Remember that I explained this trick the other day, that we should have a factor to go forward on the point. Otherwise, you're going to always be constrained to the very edge of the wall, and that could be bad. So I need this variable. I didn't put it. It's a float, and for now let's put a fixed value because I don't have time to control this value from outside, but I don't know, let's put it like 5, and later if I have time I will put here some function where you can play around with this number. Okay, so what else do I have here? Yeah, so at the end, if I do this, I have this local position. And then this local position, I'm going to divide it by the delta to get the normalized position, and I'm going to multiply, round it to remove value. Oh, well, yes, because the delta already has the dimensions. And I'm going to find the row using this to know which is the row in all the pixels using the dimensions. And then finally, I'm going to construct this UV where I'm going to find the number of probes. By the way, I didn't pass the number of probes, I think. Okay, so I have a UV. Okay, this UV, by the way, you can see it's the row UV. For this is going to tell me which from top to the bottom what is the line that contains this prof. Okay, I can put this, by the way, in a function, which is going to look much cleaner. So something like this. I know I don't have too much time, but it will be way cleaner. So now let's copy this part of the code. Now I know the row. I have to read all the spherical harmonics. Okay. So what I'm going to do is I know that there's 9, so the UVs go from 0 to 1. So 1 divided by 9 will be the offset between every value. I'm going to do it 9 times. So I'm going to construct this UV that has the row UV of the row of the profs that I want to read, and this delta I computed before multiplied by the number, the coefficient of the prof I want. So the first one will be 0, the next one will be 0.1, 0.2, or something like that. Okay, and then I'm going to go to the textures, prof textures, read this coefficient, get the color, and put it in this structure that we were talking before, this SH. And once I have this SH, I compute the irradiance, passing the normal, the SH, and boom, I have the amount of light. So I can just write this down. The right way to do this would be to take the albedo, SYZ, and multiply it by the irradiance. Okay, and I'm going to put vector 4 here and put the alpha to 1 so it doesn't complain. Okay, so I think this should be enough to have some sort of irradiance rendering, and it's going to be accumulated on top. But for now, if I don't want to accumulate it on top, I can disable the blending. So if I disable the blending, it will not add on top of the scene. I also like usually to have a multiplier, irradiance multiplier, in case I want to see if it looks good or not. So irradiance multiplier, I'm going to put this variable on my renderer, so I can multiply the amount of light I want. It looks good because then if there's something strange, I can debug it. So it's going to be this here. By default, the multiplier is going to be 1. I don't want to multiply it a lot, but on show UI, I have this radius here, so I'm going to put here also this one. Okay, so if in any moment I want to add more irradiance, I'm going to pass this as multiplier, and I'm going to use it here on my shader, multiplying the irradiance by this beautiful multiplier. Remember that this could be negative, so always clamp it, so if it's bigger, it doesn't go negative. And this multiplier, I didn't put it on my variables, so okay. That's it. It's ready. I hope it works. If it doesn't work, I don't have too much time to debug it. I'm going to disable the blending now because I want to be able to see only the irradiance. I don't want to see all the other colors. And even though maybe I don't want to multiply it by the albedo. Where I was multiplying by the albedo? 1 second. No, it's here. I'm not going to multiply it by now. I'm going to comment it because for debugging it's better to only have the irradiance without anything else. Okay, so let's see what happens. As I said, it's very likely that it's going to crash the first times because probably I didn't pass some variable or something to the shader. It's crashing already on the shader, and it's crashing because some variable doesn't exist. Here there's so many extra texture. Yeah, that's right. I didn't upload the extra texture, so this doesn't exist. Next one, world pause, restart. Why is comparing by the second one? Delta. I don't have delta. Yeah, I don't have delta. I forgot to put it, but I think that delta can be computed from the. Sorry, 1 second. Delta was end pause minus start pause divided by the number of values. Yeah, so this one I can make it on the shader manually. So apply irradiance. I remember last year I did it wrong. So this one, it's irradiant cache and irradiant cache start, and divided by irradiant cache dimensions, dims. Okay, this delta. It's nice to always to pre-compute these things outside, and you pass it to the shader. It's always better to do that than do it inside. If you can do it outside, you save some computations. So here, here delta, it's a vector 3. So here with everything else, I have to put this one also. Okay, so I have now all the parameters I need to compute, and I don't think there was any other error. And delta didn't exist, and well, let's try to see what happens. I'm not sure it's going to work. I think there's still an error on the shader. I don't know if anybody is still alive on this long class. As I said, this is a long topic, and also for me this is more interesting because, as I said, nobody explained this to me. I have to learn it from reading a lot of things, and it's always nice to have a solution that's more like modern. So here it's complaining because world pause is not defined, but I define it. I say world without the underscore. Sorry. Okay. Cool. So let's see first. We have props here. Yes. We still have the crazy ones I computed before, so I'm going to recompute them now with less crazy values. So here we have the normal ones. And the function to compute the irradiance, I'm not calling it. Well, I'm calling it, but it's commented. So that's going to be necessary to enable this. If it works, it will be a miracle. Okay, compiles, and it crashes. It crashes. Oh yeah, it crashes because I don't have this texture, prof texture. So if I don't have this texture, there's nothing to do, because this texture only appears when you load it. But when you're launching the application, it hasn't loaded this text, the Irradiance cache yet. Although I could load it at the startup of the application, but for now I'm not loading them, so the props texture is empty, so it's null, and I'm using a null texture, so it crashes. That's the good thing about putting null. If I didn't put null, when I initialize this variable, it will think that it's a texture, and whatever happens. Okay, so load them. And we have something now. Okay, it's a little bit mixed with the rest of the illumination. So, yeah, it's strange that that it's here, because there's something that I mean, I shouldn't be able to see the house, because if I'm rendering a full screen quad and the quad is not blended, I don't understand why I can see this light or this other light. Maybe because it's applied afterwards. Let me see. It's being added. Yes, you're right. I forgot. I'm computed before the lights, and because I computed before the lights are adding up. I don't want to compute before the lights. I want to compute it after everything. Here, this way is going to cover all the scene with the irradiance. Okay, because otherwise I can see it. I'm rendering the irradiance, and then I'm rendering the lights on top of that. So that's why I see the lights. I only want to see the irradiance now. Okay, so boom, boom, boom. Here we have. This is the radiance. Okay, and I'm not interpolating, so you can see it's horrible, but it looks nice. I mean, as you can see, there's some irradiance in some areas. Let's try to play around with this now. I'm going to take the let's try to do a test. First of all, I want to put the irradiance back as like a blended. Otherwise, I won't be able. I can have a function here to say show only irradiance or something like that. But for now, I want to see the irradiance with the scene. But as yeah, I can do this. I want to see the irradiance with the scene. I'm going to try to put an object that is very emissive, like I did before, and try to see if that illuminates with a little bit of ambient the rest of the scene. Okay, so I'm going to take this sign here, and I'm going to move it. By the way, there was a huge error on my code related to rotations and stuff like that, and that's why sometimes when you rotate some objects, it didn't work well. And I fixed it today, but it's not on the repo. So, okay, so I'm going to put this object, which is emissive, remember. This object has emissive. I'm going to put it here, so it's going to emit light over here, if everything goes well, okay? So let's update the profs. If it doesn't work, I will try to do another hack. Okay, and you can see there's more light on the scene now, and there's a little bit of light here. Hard to see with the profs because, well, now the profs are being rendered with blended. Damn it, I had to disable the blend when you render the profs. But I want to exaggerate that more. So first, I can go to this irradiance multipliers to multiply it. So you can see I can put more irradiance if I want to. Also, this irradiance has the ambient light. I say the ambient light should be removed when you render the irradiance cache. I didn't do it, so that's one of the reasons why there's so much light. But what I want to do is, if I take, for instance, this yellow thing here, and I go to the sign, and I found this yellow thingy, probably it's these neon arrows. I don't know. Probably if I move them around to see if it's this one, yeah, this one over here, I'm going to make them ultra bright. So I'm going to go here and say, hey, this is going to be 100, 100, and 20. Okay, so now I'm going to compute again the profs, and let's see what happens. You can see, oops, sorry, I moved this. You can see how this is illuminating with emissive light, something that we didn't have before, okay? But obviously, we are not interpolating, Secondly, we are not taking the density of the props is very small. You have to put more props if you want to have more detail. Okay, but we have something that looks like irradiance that forces the system to take into account when there's objects that are emissive light that also takes into account. It's static, but it's not so super slow, and we can load it from a cache very fast. Okay, so we accomplished what we wanted to do. Just a final point. Sorry for how long it is. There's more ways to improve this they are on the slides. If you have some time, check the slides. And another thing I want to say I forgot to mention before, sorry, is that currently, if I generate now the props again, if I do the update props, in this case, when I updating the props, I'm using the forward render. And the forward render, remember, if I go here and enable the forward render, and the forward, oh, damn it, it's broken. But anyway, the forward doesn't take into account the irradiance. So it's okay. I mean, when I generate the irradiance, I'm using a version that doesn't use the irradiance. But some engines like to use the irradiance from a previous iteration on the next iteration. If you do that, you can make the system simulate like the light is bouncing many times through the scene, but you can end up with too much light. Okay, so you can play around with some coefficient where you multiply this multiplier by, I don't know, 0.5, and you generate it again using the irradiance. I don't know, there's many hacks that you can try to do, but they're explained on this on the slides. So read them, and there's much more that I have explained in this class. And you have to implement this, and you have to implement it with interpolation, by the way. Okay, so that's it for today. Sorry for taking so much. I hope that you enjoyed this interesting approximation to irradiance, and see you next Monday with all the doubts about this topic. Okay, if no questions, bye bye.